Talk about domain-driven design, but really, for the most part, this is talk about F# and more generally functional programming. But I talk about a domain that you would typically implement with C# and ORM, like SQL, and I'm going to talk about how the F# implementation contrasts, what are some of the benefits, and what are some of the challenges that I faced. And I've been using F# heavily for the past year. For the past 8 months or so, I've been using F# exclusively, and I almost refuse to look at C# and do anything in C#. So I've been fortunate to be able to do that. And I originally looked at F# several years ago, but didn't really get a chance to start using it in production until this past year. And this original talk I made a year ago. And so it's going to include, I'm also going to include things that I've learned since. But for the most part, everything still works, everything still applies. So it's just another indication of how powerful F# can be if put to good use. So let's see here. I guess the goals of the talk is to learn some F#, functional programming, learn a little bit of event sourcing, and contrast that all to traditional object-oriented approaches. How many here are familiar with event sourcing? Okay. How many are familiar with domain-driven design? Okay. And then F#, obviously most. So I don't really have a set structure, or I guess to put in other words, there's too much material that we can cover here. We won't fit into one night. So I'll use you guys to sort of guide me with what's more interesting. Because I could spend the whole night talking about F# specifically. I could spend the whole night talking about event sourcing. But I think we'll just cover a little bit of everything. Let's see. And this is how it all ties together. Is you have domain-driven design, and this is what you use to express your domain model. How you model your domain, how you partition it into separate contexts, and refine the language that you use to describe your domain. And functional programming comes in where you are able to express this domain model in code somehow. So you can either express it in C#, or you could express it in F# or using the functional paradigm. And then event sourcing comes in for persistence, and it's very naturally aligned with functional programming because it's all about immutability and streams of events, streams of things. So persistence is implemented with event sourcing, and then all of this sort of coalesces into a Cqrs style of architecture where you have your domain model executing commands that emits events, which are then used to implement your query store. So you have a segregation between your commands and your queries, which is also quite natural with event sourcing and functional programming. In functional programming, there's actually a few core themes, in my opinion, that everything else depends on and everything else emanates from. And we're going to be seeing how all of these themes begin to make sense, how they apply in specific cases. So I'm going to actually walk through an implementation of an event-sourced domain model using C#, and I'm going to compare that with a F# implementation that implements the same exact domain, but in F# and a functional style. The things that constantly come up with functional programming are these three things, in my opinion, and they kind of all interrelate upon each other, and there's other things that kind of depend on these, but it's all about immutability. So you instead of changing state, you simply return a new value, and the other one remains unchanged. And this comes up a lot in functional programming. Purity, and this is a bit of a subtle concept, but the idea with purity is that you can look at your code and you can factor out parts of the code without really changing the meaning because you try to avoid side effects. And another way to think about that is everything that a function does should be captured in the type signature of the function, as opposed to something like a void returning function, which really hides what's going on, and that's completely impure because you can't replace a call to a void returning function with void because you don't know what that function does. It may do something that causes a side effect that your application depends on. And then all these themes sort of feed into this final theme of composability. And we always talk about composability in an object-oriented setting, is that you favor composition over inheritance, all this and that. But I really feel like with object-oriented programming, you reach a wall to where you can't really make things more composable, and you kind of stop there, and you simply just brute force your way through the design. And I'll discuss exactly how this comes up, but in my opinion, functional programming allows your code to be much more composable and reusable because of immutability, because of purity, and we'll see exactly how. Let's see. All right, so this the domain that the example is based on is a fictitious inventory tracking system. It's really based on this Cqrs example that Greg Young has put out many years ago, actually, and it's a model that sort of is the cornerstone of an event-sourced implementation in a language like C# or Java. All other implementations are some variations of this. And this is just a simple inventory tracking system. It has the following behaviors, so to say. So a term from domain-driven design is aggregate. It's a little bit of a confusing term, but it really sort of means it implies like an entity that you're dealing with. So in this case, we have the concept of an inventory item, and this is our aggregate. This is our aggregate of behaviors and events, sort of a conceptual whole that we refer to. And in this particular case, we have an inventory item aggregate, and it has the following behaviors. We can create inventory items, rename them, activate them, deactivate them, check items in, check items out. Pretty simple. And it's good for an example, but it doesn't mean that the model I'm going to explain and demonstrate is only good for simple examples, and I've actually had the opportunity to test this out in a production setting, and it all works great. And that's one of the benefits of functional programming, is that you can start with a simple implementation, and then you get this feeling like, well, am I really done? Is this it? And it actually works, and it's done. You're missing 10 or 15 factories and builders and whatever other patterns you have in object-oriented programming, but the solution is simpler and easy to think about, easy to refactor. So we'll see how that goes. Let's see what else we have. So we'll start with the C# example. So this is an inventory item in C#, and this is only part of the class, as you imagine, but it only shows the deactivate behavior. And this is a very typical implementation in an object-oriented language, specifically for event sourcing. So we have a deactivate behavior on an inventory item, which ultimately sets the activated field to false. But the way it does it is the deactivate method first checks an invariant. If it's already deactivated, it throws an exception saying you can't deactivate a deactivated item. And you can think about this more generally as being any sort of business logic that you run before applying the behavior. And then the next thing that happens is you apply the change. And this is a little bit counterintuitive to how things happen, but basically what happens is you add an event to this aggregate saying that the inventory item was deactivated. And what happens is this method in turn calls a method on the base class, in this case aggregate root, and then it comes back around to call this method here. And this is done this way so that when you reconstitute this aggregate from an event store, your repository will simply call this method as it's reading all the events, and that way you can bring the aggregate back to its final state by replaying all the events that have occurred since the beginning. And this is a concept from event sourcing, which we'll cover more in more depth later on. But that's the gist of it, and this is the basic C# implementation. And I have. Oops. have more of the code here. So this is generally what the class looks like. You have a method for the behavior, a method that applies the state change, and this happens for all the other behaviors: change name, remove, check in, and then you have your other typical thing on an aggregate, which is the aggregate ID. So that's pretty much it for this aggregate. It's really simple. Really only has one piece of state, which is a boolean that indicates whether it's active or not. Now, this is the aggregate root base class. So it has the version, has the ID. I guess it doesn't have to be on the subclass. And this is where the event goes to. So in the previous slide, you saw that. You saw the apply change method. Well, this is it. It basically, this line of code uses some dynamic DLR voodoo magic to go out to the subclass and actually call the apply method on there. So this is this apply method. And then it adds, this is if we're not replaying events, it adds it to the list of changes that have occurred. And so this object keeps a list of events that have occurred since it was reconstituted, and when we go to persist it, we simply read all these events out and save them to the event store. So it's a way of explicitly tracking the changes that happen in your aggregate, which is quite a bit different from what you would typically do where, with an ORM-based implementation, your behaviors change the state of the aggregate, and then you persist that state. Whereas in this case, we're persisting the events because we know we can always replay the events to arrive at the final state. So again, basic C# implementation, nothing special really, and you don't really need much more than this.
Excuse me, the reference to is new that's not whether you've got a new object, that's whether you're playing an object, whether you're playing things back from the event store rather than...
Yes, so exactly. And by the way, anyone, if you guys have questions, just stop me. So when we call the apply change method after we've verified that the business logic is okay, so in this case, we verified the business logic, then we call apply change, and we say is new true. So that means that this is a new event, and that's why we add it to the collection of changes. Whereas if we're reconstituting this aggregate, it's not a new event, it's an existing event. So in that case, we're not adding it to the list of changes, but we're simply going to apply the change. So some of the issues with this code are the following, and so I'll talk about all these. Number one is it's quite verbose, and it's not really an issue in and of itself, but I really think it begins to add up. And in a typical C# solution, you have a class per file, and you have subclasses, and it gets, in my opinion, to be very cumbersome to look at a single piece of functionality because it's spread across multiple classes, and you have to reach into a base class. So it's quite verbose, and it has to do with C# more so than anything else. We have public namespace, this, that. It's quite verbose. We have to be explicit about type signatures everywhere, and it really begins to add up, but not a huge issue. Next one is that the implementation that we just saw, it's not a POCO, so it's not just a simple C# class, this inventory item. We have to inherit from an aggregate root class, and this is to enable the event-sourced implementation. Now, you could try to do something fancy and avoid this base class and maybe use some sort of aspect-oriented framework or something of the sort, but it's not going to be pretty. And again, this is a consequence, in my opinion, of the object-oriented approach. The next issue is the dynamic DLR, the magic that had to happen in order to call the apply method on the subclass, so that the aggregate root base class is calling a method on the subclass. And there's, again, many ways to do that, but the point being that you can't do it easily. You have to rely on reflection or something of the sort. The other issue is conflation of state and identity. So as you saw in this class, we have both state that's related to the inventory item itself, whether it's activated or not. But then the identity is a different concept because the identity really has nothing to do with any of the behaviors on the inventory item. None of these behaviors do anything with the identity. And this is what I refer to as conflation of identity and state, is that we have this one concept of an identity of an aggregate, which can also include things like the version or the last updated date. And if you manage them separately, if you create your system in such a way that identity and all those things are managed in one place and the behavior is another, it makes things simpler overall. But doing that in a C# implementation becomes prohibitive, becomes overly complicated. And then finally, there's broken composition. And this is what I mean by this is that when we look at this method, deactivate, the reason I call it broken composition is that it reads good and it's easy to call this method from your code, but in order to have this method be called in an automated way, you have to either rely on reflection or do something else. But the problem with this method is you have a deactivate method. Well, you have to have something that calls that method explicitly. So you would typically have an application service or a command handler which receives a command, deserializes it, and then reconstitutes the aggregate, calls the deactivate method on it, and then persists it. Well, the issue is that this pattern repeats for all the behaviors. If you're changing the name of an item, you do the same thing. You reconstitute the aggregate, you run the behavior, and then you persist the events. And because we've called this method change name and remove and check in and deactivate, that means that we have to call those methods explicitly. So we have to have a corresponding application service method that calls this method in turn. And on the one hand, this is good practice of domain-driven design because you're really associating, you're really expressing your domain model in the code. Well, we can deactivate an inventory item. Well, we put a behavior called deactivate on it, and that's great. But to make this reusable, it breaks your composition because this is no longer composable. You have to explicitly call this method. To make it more composable would be where you could have just an execute method that accepts different types of commands, but there's only one execute method. And doing that with a C# or an object-oriented language is also prohibitive because you end up having to do something like what's that pattern? The visitor pattern. So since you don't have double dispatch, you can't call a specific method unless you either cast your command to that specific type or you have the object itself call the command that it needs. And none of those approaches are great. So that's what I mean by broken composition. Any questions? All right, so let's see here. So I'll walk through the F# implementation. I'm not really happy with the way I organize these slides. So I'll be sliding back and forth between the actual code. So this shows a part of the F# implementation. Specifically, in the F# implementation, which is actually vastly different from the C# implementation. We don't have a notion of a class. You have a notion of a class in F#, but I don't make use of classes in this case. It's all about immutable state. Functions are contained inside modules, and they simply return values without changing the original value. So what we're abstracting here is the state. So as you remember from the C# implementation, the only piece of state we had is a Boolean indicating whether the inventory item was active. So here we are. This declares a type in F# that has one property, is active. And this is called a record type. And it's very similar to a C# class. In fact, it compiles to a regular C# class, except this becomes a property, and it becomes private set. And the generated class has a constructor that has basically accepts all the values in the constructor and sets them. And you know, you can't have inheritance with the record types in the F#, so you can't have another record type that inherits from this. Again, immutable by default. And this is a really big win here, is that the F# compiler will actually auto-generate structural equality and comparison. So the resulting C# class would implement IEquatable and IComparable. And this is actually really important because in F#, you don't really rely on reference comparison or reference equality, but instead you rely on structural equality. And structural equality is simply the idea of comparing two values based on their values. So two state values would be considered equal if their isActive fields are equal, not having nothing to do with their location in the heap or the stack or whatever. So this is a very powerful concept in F#, but we also have something very similar in C#. It's just you end up writing a lot more code to do the same thing. Now let's see, moving on. So this is an example of a type that we don't have in C#, and this is, in my opinion, one of the big ones that sort of causes the F# code to be a lot cleaner. And this is called a union type. You might be familiar with union types from C or something of the sort, but really there's nothing like that in object-oriented languages. A union type is it defines a value that can be in one of several cases. So in this case, we have a type called command, and it has two variants. It has create and deactivate. And a command could either be create or deactivate, and that's it. One way to think of it is it's almost like an enum in C#, but a lot more powerful since you can actually associate more data with each key. And in this case, the create command is something that also carries a field, specifically the name, because when we're creating an inventory item, we're going to name it. And then the deactivate command has nothing on it because there's no information. It's just deactivate, and that's it. How these are actually implemented, or what they compile to, is you have an abstract base class called command, and then you have inner classes, which are subclasses. So you'd have an inner class called create that has one property called name, and then you'd have another base class or subclass called deactivate. And this a very powerful concept because F# it enforces that when you're processing a value of type command, the compiler forces you to handle each case explicitly. And this is something you don't get in C# in any possible way, other than using an enum of the sort. You might get a warning from the compiler in a switch statement. But in F# you actually have to handle each case explicitly. And this has a tremendous number of benefits, because in C# you could create a bunch of classes that represent commands, but nothing enforces your code to make sure that it's handling all these commands. In F# you do. And so in terms of domain-driven design, this becomes a powerful concept of actually modeling the domain. A lot of times when I start thinking about a new domain, I'll start with thinking about the commands and events around that domain. And this is to me the most abstract way that you can think about a domain. It's just a black box that you can send commands to, and it emits some sort of event. So in this case it's pretty simple. You can create an inventory item, and the resulting event is inventory item created, also having a name. Same thing for deactivate, deactivated.
I have a question. So wouldn't there be times where it wouldn't make sense to have certain commands on certain types of aggregates? So for example, an inventory item might have create or deactivate, but deactivate may not mean something for a different type of item, like a shipment or something like that. So you wouldn't want to check that command, I would think.
Well, in that case, you would have a different set of commands for the other.
For that other aggregate.
Exactly. So I mean, you kind of structure your code such that if you have a union type, then you use it in a very specific place, and if you have another domain, you simply create a new union type, and they're very cheap to declare. I mean, this is it. As you can imagine in C#, this would require 3 classes and probably 3 files, and a lot of boilerplate code that is very not interesting because all you really care about is that, you know, this is the create command, this is the deactivate command.
Just to clarify, this is the CQRS design pattern you're applying. If you were solving a problem where CQRS wasn't the appropriate architectural pattern, then you wouldn't necessarily do this.
Well, in fact, I think you would, and I'll actually explain exactly why.
Okay.
I'll explain exactly why. So yes, I mean, this is this hints at the CQRS pattern in that you have commands declared here, and then you have events, and then the query side is based on these events. So you have a separate part of the system that listens for events and denormalizes them into a queryable form. Now, that's one way you could go about this, but it doesn't force you to use CQRS, because you can actually use this same implementation and persist into a SQL store and query that SQL store for your queries. So you don't have to.
Let me go a little further than CQRS and EventStore. I mean, there's
yes,
something
exactly. Yes. So EventStore definitely. So event sourcing is this is very indicative of event sourcing. But again, the actual F# implementation doesn't have to be based on event sourcing. It doesn't have to run on EventStore. All of this code that I'm showing you is going to run exactly unchanged if it's run using a key value store or even a SQL store. And once we get to the code, I'll show you exactly how. But again, so this is commands. This is a more complete example of the commands. You know, this is the command type, event type. This is our state type that we saw. And really, this one file is how I typically structure the aggregates. Is that you have, you know, the single file. This declares a module, and a module is just like a static class, basically. Corresponds to a static class. And then inside here you declare your types, and then this is your apply function like we saw in the C# example, and then this is your execute function, which correspond to the behaviors. Now I'll get to this in more detail in just a second. Right, so union type, kind of covered all this. Pattern matching is sort of like a switch statement, but far more powerful, because you don't just match on a predefined value, you could match on patterns of data. And that's the technique you use to actually process values of union types, is you pattern match on the different cases, and you have specific behaviors for each case. Let's see. So, let's see, this is not, let me just show you this instead. So, here's an example of pattern matching. So, this is a function in F#. The name of the function is apply. This is the first argument of the function, which in this case is the inventory item. And the type of this value is this piece of state here. So that's what the type of this value is. F# has a very powerful type inference system in place, so that you hardly ever have to annotate types on things. And again, this is something that you can play with, because if you don't annotate the type, as I've started to annotate more and more, because it makes it easier to read the code later on if you explicitly annotate it. So if you annotate it, it would look something like this.
Can you make the color a bit bigger?
Oh, yes.
That's like you my cursor.
Let's see.
Right.
Yeah, Sublime is a little strange about. Yeah, I'm having a little technical difficulty here.
You threw off his whole presentation. That was his plan.
Yeah, I'm at a loss here. I'm sort of new to this Mac that I got. But unfortunately, well, actually, let me try this. There we go.
Oh, you do it. There it is.
There we go. Is that better? All right. All right, so back to this apply function here. So it's a function that takes an argument state. Now, this is a little tricky. What this syntax means here is that this function actually takes another argument after item, and in this case, the argument is of type event. And how F# figures it out is it says, well, I'm matching here on all these cases which match this event exactly, so it knows that the second argument of this function is actually an event of this type. And so what happens here is that this is a function that takes the current state represented by this item value here and some event and basically changes the state in response to the event. So in case that the event that we're handling is a created event, what we do is we take this item and we change the isActive field to true. Now this line of code is basically built-in syntactic sugar that F# has that allows you to take an immutable value of, in this case, of a type state, copy all its fields, but only change one field. Now, in this case, we only have one field, but let's say that state had a bunch of fields on it and we only wanted to change the isActive field. This is how you would do it. You would take the current state and return a new state with the isActive set to true. So this syntax returns a new value of type state. And the signature of this function is basically something that looks like this. We take the current state, we take an event, and we produce a new state. And we'll see why this signature is very important later on and how it fits with event sourcing. But anyway.
Is there a way to annotate that the result is going to be a state, or is that always the case when you have a method that takes an argument of a type that it's going to return the same type?
You can yes, you can annotate. So for example, if you wanted to be explicit about your arguments on this function, to annotate that the result type is also a state, you would say this. And actually, it's something you do quite a lot. Is sometimes you're not really sure why the compiler is complaining, and what you can do is you can annotate the function explicitly, and it'll tell you why it doesn't necessarily fit that signature. And so the other thing is, if I took this code and somehow, for some reason, I wrote this function, but I didn't, I forgot to handle the renamed event. The compiler would complain, this code wouldn't compile. It says, well, you're not handling the renamed event. And this is very powerful because there's no way you can really do something like this in C#. Anyway, so we have, this is how we're handling all these events. And this corresponds to, in C#, these apply methods. So we have apply inventory item created, apply inventory item deactivated, apply removed, all the events that you apply. And this function is called when you're replaying all the events to bring up your aggregate to the current state, so that all the past things that ever happened are run through this function again and bring the current state up to date, and then you can execute the behavior. So based on just this, what we've seen so far, I feel like there's a few improvements that the F# implementation has. It's a lot less verbose, and again, this one is not hugely important, but I really think that after a while, it begins to grow on you. Is that there's a lot less code, and not just code, there's a lot less noise, there's a lot less boilerplate, and it's just visually less cluttered. You have one file that you look at, and it has all your events, your commands, all your behaviors, everything about the aggregate, whereas the C# implementation is split across multiple files. You have your inventory item class in one place, you have your aggregate in another place, and then you have all your commands and events probably in individual classes. I mean, they could all be in one class, but now you're already talking 3+ files, and it becomes cumbersome to look at them all. The other thing is explicitness, or being explicit about what goes on. So, as we looked at earlier, the signature of this function is very explicit. It takes a state, takes an event, produces a state, and that captures everything about this function. There's nothing else that happens inside here. It doesn't call any side effect in code, nothing like that. Whereas the C# implementation, this method is actually very deceptive, because you say deactivate, but it doesn't return anything. So you have to assume that it causes some sort of state change, but it's not really evident until you either pull the event out or actually inspect the state. So it's not really evident from looking at this signature here what happens in the function. So it's very implicit. It's implicit that the state is changed, that the event is added, and having known that, you can kind of get used to it, and that's what you assume, but you won't know that directly from looking at the signature. Uniformity. So this is the idea that I was talking about earlier, where I was arguing that this C# implementation breaks composability because it's non-uniform. Because we have a deactivate method, we have a change name method, and these aren't uniform because they're different names, and so you have to call them explicitly. Whereas with the F# implementation, there's only one apply function that, instead of taking a specific event, it takes all the events, and it forces you to handle all these events. So I also think this is a benefit, because now you can actually abstract over this. Now you can have an abstract concept of an apply that takes an abstract state, abstract event, and returns the corresponding state. And you can call this function from a framework. You don't have to have an explicit method call to a created apply or any of those. You can just call a single apply. And this makes the code a lot more reusable. You can fit it into a framework and get rid of all the boilerplate code you'd have to have with C# by having a specific command handler that calls the created apply or the create behavior.
I have a question with that.
Uh-huh.
So the user is calling apply directly in the F# code, unlike calling the feeder method like deactivate in the C# code?
No, so we'll get to the actual code that calls it, and the part of the F# code that calls the apply method is the part that's reconstituting the aggregate and bringing it up to the current state. So it gets all the events for this aggregate and applies each of them. But the point is that code that's doing that doesn't have to know about a specific aggregate type. All it has to know about it is the existence of some apply function. Whereas in C#, you have to have, the aggregate calls the when method by passing in the event. So the aggregate, the repository can be made abstract, but the command handler cannot be. And we'll see how the command handler looks in C#. And so you don't really call the apply method directly, you have the framework do it for you. All right, so what's next? And then, again, as far as domain-driven design, the benefits of the F# approach are that you focus on your behavior by reducing the clutter and really making these types very cheap to create. I feel like you can focus on the behavior of the aggregate as opposed to the infrastructure required to implement it. You're not thinking about abstract classes, dynamic dispatch, any of that. You're just thinking, I have some commands, I have some events, and I have some state that I need to maintain in order to check the invariance. And that's it. And then I have my apply, and then I have the execute. And we'll get to this in just a minute here. So that's one of the benefits for domain-driven design, is that you're not really thinking about your entities as in a CRUD type of fashion, create, read, update, delete. You're thinking more about the behaviors that surround this aggregate. And that's very important for domain-driven design. The other benefit is that the resulting code is more declarative. And this is, again, a byproduct of functional programming, because, again, we're talking about the specific behaviors of the inventory item aggregate. We're declaring what happens. It's sort of like, instead of writing code, you're declaring an equation that describes how the code runs. You're almost declaring a specification And then you can think of F# as something that actually implements this specification. The code is more assertive, which is another benefit for domain-driven design, and side effect free. Now, all these things, all these benefits are actually listed and discussed in the domain-driven design book, in the original book by Eric Evans, and then in the new book by Von Vernon. These are all tenets of domain-driven design: side effect free functions, declarative code, assertive code, and in the book, reading the book and rereading the book, it's almost spooky, because it's almost as if Eric Evans has reinvented functional programming for enterprise software, because all these things that make a great deal of sense in functional programming are what he discusses for domain-driven design, which was targeted for Java, C# type of implementations. But we all get them for free in F#. Now, the side effect free thing, I talked about it briefly, how this function doesn't incur any side effects, and none of the functions in this inventory item module cause any side effects. They simply return whatever they do, and this way we can capture the behavior of the function in the signature alone. So let's see. Now, to pause for a moment and discuss some of the challenges. And this is something, some of the challenges that I've faced, and I'm sure other people face as they're starting to use F#. It's a new paradigm, and the new paradigm is functional programming. When I first looked at F#, it looked pretty cool, and I started using it. But what I was doing is I was doing C# and F#. I was looking up the syntax for, well, how do you declare a class? How do you inherit from a class? How do you mutate a field? And if you can do that in F# and it's fine, and it's just as good as C#, but for me it wasn't enough to make a shift to F#. So that's one of the challenges. And functional programming, as compared to object-oriented programming, is a lot deeper of a subject. There's a lot more research that's done in functional programming, and it's because you can really formalize functional programming in a mathematical way that you can't do with object-oriented programming. And many have tried, and in fact there's proofs that indicate that the object-oriented model that we tend to use, such as C# and Java, are simply something that we can't formalize, and it's just it works because we hack it together, but it doesn't allow us to draw on a lot of the research that gets done on functional languages. The next challenge is that F# is a completely new syntax. It's vastly different from C# and that whole family of C-like languages with the curly braces. And this is also pretty important, because if you're going to be reading a lot of code, which is where you're going to be doing most of the time, it's nice to be able to sort of see it right away, as opposed to having to check the individual characters and then individual function calls. And it takes a while to get used to with F#, especially since F# does a lot of type inference, and a lot of times it looks more like a dynamic language. But there are types, and you have to kind of know what they are, and it takes getting used to. The next challenge with F# is that it is a language that supports both functional and object-oriented programming, and a lot of times you feel like you don't know which one to choose. Like, you have so many options, and sometimes they almost get in the way of one another. Sometimes a class is better, sometimes a function is better, and it can get a little confusing as compared to a purely functional language like Haskell, where you don't really have this object-oriented side of it. So it can be, it can make it more confusing. There is less tooling support. So, as far as Visual Studio, there's very little syntax highlighting. I think it only highlights strings, quoted strings, and keywords, and that's it. That was a little bit strange for me coming from C#. I wanted a little bit more color on the screen. The bigger one is there's no refactoring support, so there's no such thing as find all references or rename or any of that. But on the other side of things, is you don't really rely on those things as much. You have far less code. I mean, I think orders of magnitude less code, and everything is a lot more type safe. And so you can rely on the compiler a lot more instead of relying on the tooling. Many people are of the opinion that overinvestment into tooling indicates a smell. It indicates a smell with the paradigm, with the approach that you're using, and it really begins to make sense after having programmed in F# for a while, is that you really rely much less on your IDE and much more on the compiler and the language itself. Another challenge with F# is that C# interop can be tricky. Now, it is fully supported, and you can access a C# assembly from F# and vice versa, but the types are different. So, you know, there's like a canonical F# list, which is an immutable list, a lot more like the linked list in C#, a lot like the cons list in Lisp, and you know, a lot of functional languages. You don't really have that in C#, so in order to export that list, you tend to convert it to some sort of C# list, or you can even export the actual F# type, but then it's not really convenient to use from C#. So this is something that can be tricky. A lot of times when you're referencing a C# library, you'll end up creating a little wrapper around it in F# to make it more convenient to call from C# or from F#. And then the other challenge with F# is that it's missing some of the more advanced features available in other functional languages. And this can be a little bit frustrating when you're trying to make your code more abstract and more reusable. One of those things is type classes, which is present in Haskell. Now, type classes themselves don't really have anything to do with functional programming, other than that they're a mechanism used in Haskell. And one way to think of type classes is they're sort of like extension methods in C#, but it's as if extension methods allowed you to actually implement an interface. So by adding extension methods to int, you could actually have int implement an interface without having to create a whole new type implementing that interface. So type classes sort of allow you to do that. And something like a language like Scala, for example, doesn't have type classes, but it has another mechanism to support the same kind of behavior. And this is a big one, higher kinds. And this is sort of like so generics. We have generics in C# and F#, but the problem is that you can't abstract over types that are themselves generic. So you could say, I have a function that takes some sort of type T, or a class that's parameterized by a type T, but you can't say that, you know, this type T is itself a type constructor. You can kind of do it with
Constraints can help a little.
constraints a little bit, but it's very limited because a constraint has to be bound either to the same type. So you could say where T is an IEnumerable, but IEnumerable of what? So you have to pass another type, whereas higher kinds are sort of like types for types. So you can have a type constructor which takes a type, produces another type, or takes two types. And so it's sort of like you're thinking about functions, but at the type level. And this is something that it's not really strictly necessary for functional programming, but it can make your code a lot more reusable. But you know, since the code in F# is already so brief, it's easy enough to just rewrite the code for a specific type. And we're not really going to get into any of anything that requires this, so you can kind of ignore it.
Is that not covered by the relatively new contravariance and covariance, I guess, is the opposite?
Yeah. Well, so covariance contravariance is actually more. First of all, you don't have that in F#. You don't have covariance contravariance on generics. You do in C#, but covariance contravariance is something that it certainly doesn't solve the problem solved by higher kinds. And in fact, it's more of an indication of another problem. It's sort of like when you intersect functional programming and object-oriented programming, you sort of create a requirement for variance and covariance. But a lot of times in functional programming, you don't really even deal with it, covariance and variance, because in F# specifically, it's easy enough to actually convert a value to the proper type before calling a function, as opposed to having that be inferred. So I haven't actually seen that be an issue. And but to follow up on that, F# does have this concept called statically resolved type parameters, which allows you to sort of do duck typing, but statically check it. You can actually accept a function of type t in or a value of type t in your function, and you could say that t has to have these functions. So you're not saying that t inherits from some interface, you're saying that t has these functions. And then you can actually call these functions. And that's actually another powerful thing in F# that you don't have in C#, and it can be used to emulate type classes. It can be used to almost emulate higher kinds. It gives you a lot of the same functionality. And in the language itself, these statically resolved type parameters or type constraints, they're used to implement like generic addition and division methods that operate on ints or doubles or decimals or anything like that. So again, nothing quite like higher kinds, but you have other things that get you almost there. All right, so the next few slides are going to be about event sourcing. We talked about it a little bit. And it was, you know, the idea, the notion was captured quite succinctly by Greg Young. Event sourcing is just this. You have a function that takes a state and event, produces a new state. And this is what we saw earlier. We saw this function here. It takes a state, and as I mentioned earlier, this syntax here means that this function actually takes another value that matches, you know, this event. So maybe to make it more clear, this function could actually be written like this. So this is the exact same thing. The function syntax just simply assumes that you're doing this. Because you do this kind of thing a lot in F#, so you know they provide a helper.
The way it figured that out is that it saw created, deactivated, renamed as being parts of the event.
Exactly, as matching this structure here. And it does that with state too. So for example, well actually in this case, it infers the type from this value here. But you can actually do the same thing for record types. Like, you know, you could, for example, say, so this will infer that the type of this is state based on the structure here. Now, if it's ambiguous, it'll tell you it's ambiguous. Therefore, you have to qualify it. But for the most part, you hardly ever have to do that. Now, as I've programmed more and more in a production setting with F#, especially on public interface or reusable functions, I tend to explicitly annotate the types, just because while you're in the compiler, you can hover over these things and it'll tell you the type, but just by looking at the code, you can't. And you know, if you're looking at code on GitHub or you know even Sublime here, it's a lot more convenient to just be able to see the type. So I've started doing this more, but you don't have to, and you know, it just depends on how you program. So again, event sourcing, and really this is the gist of it. Is event sourcing is about, instead of persisting your state, you persist the behaviors. You persist everything that's happened, knowing that you could bring your state back to where it was by simply applying all these events. And this is what the apply function is. This is what this function is. By replaying the events, you bring it up to the current state. You can execute a new behavior, resulting in a new event, a new state. This is how Martin Fowler describes it: capture all changes to an application state as a sequence of events. Another way of thinking about it is that you capture all behaviors. Now, this is going back to the idea here, is that really this should describe the surface of what this aggregate should do. You know, everything else is a detail. Everything else is an implementation detail. And this is a good way to think about your API, so to say, is that this is an entity that handles these commands, producing these events, and these sort of correspond to the behaviors of the aggregate. Let's see. So reconstitution is you replay all the events in the past. Now, here I'll start getting into some of the surrounding infrastructure to tie it all together. We have our inventory item aggregate, and if we think about it more abstractly, you know, we can have any kind of aggregate, a shopping cart, a customer, anything. From the F# perspective, or from the implementation that we've just seen, the abstract view of the aggregate is this: we have an apply function, which is something that takes a state, takes an event, produces a new state. We have an execute function, which takes a current state, takes a command, produces an event. So this sort of corresponds to the behaviors on our inventory item class in C#. So we have a, we have our deactivate behavior, and in here we have our execute. So again, this is something that takes a state and takes a command, not an event, takes a command and produces a new event. And I'll cover this syntax and what's going on here in a second. But basically the idea here is that we have a create command, we check the invariant, and if the invariant passes, then we emit a created event. So the signature of this function is this: takes the current state, takes a command, produces an event. And this is sort of like an initial state, and it corresponds roughly to a parameterless constructor on C#. It's just something that when we're reconstituting the aggregate, we have to have some starting state so that we can apply events to it. Now,
On that apply and replay, over time, the list of events could get rather long.
Yeah.
Is there a collapse at some point?
yes, yeah. So, and I'll talk about some of the strategies of dealing with that. But basically, in most cases, you'll hardly ever have a single aggregate that has too many events, because first of all, you're replaying events specific to an aggregate instance. So you're not just replaying all inventory items, you have inventory item with ID 1.
Right, but over time, that could still get to be.
Yes, so I mean, what I found with EventStore and this implementation is that unless you have more than 1,000 events, you don't really have to worry about it. So what are the kinds of aggregates that you can think of that have more than 1,000 events in them?
Patient in the hospital.
Right. So certainly there are examples. Patient in the hospital, maybe like, you know, if you have an e-commerce platform, you could have a product that changes price quite a bit. So you could have 1,000 events there, and maybe even millions of events. And so in those cases, what you do with event sourcing is you do something called snapshotting. So instead of replaying all events, you take a snapshot at specific points. So you can take a snapshot every 1,000 events, and the snapshot is of the state. So you take a snapshot of the state, and that means that next time you replay the events, you only have to replay the events that have occurred since that state. That's how you deal with too many events in event sourcing. So not really an issue overall. And this is some F# code that kind of, so this is a function that says, give me all events of this type with this ID. And so this you can think of as a collection of events. And then to bring you up to the current state, you take these events, and this is an F# operator that basically says, take this value and pass it on to this thing on the right here. It's very similar to how you have extension methods in C# and you have link. A lot of times you'll say, where dot, select dot. You'll chain methods together. This is a similar way of doing things in F#, is that you're saying, take this value and pass it on here. Now this is a built-in F# function called fold, and it's the same thing as the link method aggregate. It basically allows you to take a collection of things and aggregate them into something else. In this case, we're taking a collection of events and collapsing them into the current state by reapplying the event. And so what we do is we take this aggregate here, we take the apply function from our aggregate, and this is the folding thing. This is the thing that folds two things into one, and this is the initial state. So given a set of events, an initial state, and a function that takes a state and an event and produces a new state, we can take all past events and replay them into the current state here. So that's pretty much it as far as actually reconstituting the aggregate. This is the integration with EventStore. Again, it's pretty simple. The load function that we saw earlier, this is an implementation of that. This is something that takes a type and an ID. This is the EventStore API. This just says, read me the stream of this ID. These values don't really matter, but basically this allows you to read the slice of the events associated with this particular ID, and then this is just a way to deserialize them. But the idea is very simple. That's the other benefit of event sourcing, is really the event store has a very simple interface. You can either write events to it or you could get events back. It doesn't really do much of anything else.
So since your function there is now impure because you're reading outside state, you
Well,
look at or something.
this is actually not true, because the impure part of your application, and this is a general concept in functional programming, is that it's not that you don't have side effects, it's that all of your application logic is declared in an impure way, and then it's like you have a run method, and that's where all the side effects occur, is that you have this shell, so to say, declared in a functional way, and it just produces values. It throws events out. You can send it commands that emits events, but it does everything in a pure way, meaning that everything that happens to this sort of shell is exposed by the signature. And then your application is what actually says, okay, I see all these events coming out here, I'm going to interpret them. And this particular interpretation is to persist the events somewhere. You could actually have many other interpretations. You could say, well, I'm just going to throw these events out. That's a different interpretation. Your logic remains the same. What you do with the resulting code is what changes. And that's indicative of all pure functional approaches, is that you sort of declare your application as almost like as a domain-specific language, and then the thing that executes is an interpreter for that language, and you can interpret it in one of many ways. So your side effects are very well contained.
In this code, is the if version supposed to be if expected version equals? Because version isn't declared yet.
Yes, exactly right. Good catch. So this is the commit function. So we had a load function that loads events. This is just something that commits an event. This is the ID. This is the expected version. It serializes it. This is an event store object. This is actually no longer required as of the new event store version. You don't have to explicitly create a stream. You can just append to a stream. So really, what you want to call is this one. And the expected version value is something that's commonplace in Cqrs. It's a way to implement optimistic concurrency. What you do is when you display an aggregate on like a website form, that's a specific version that you're displaying. And when you send a behavior to that aggregate, you send the version that you think that you're sending it to. And if something else has modified that aggregate before you did, this is going to throw a concurrency or optimistic concurrency exception saying you have a wrong version. Somebody else already modified it. So it's something that you would do in with an ORM, like in Hibernate, you have like a version property that keeps track of the version. That way, you can implement concurrency in an optimistic way in this case. And with EventStore, the version is just the number of events. It's almost implicit because the version corresponds exactly to the number of events that your aggregate has. So you start with version 0, the next event is 1, 2, 3, and so on.
I have a quick question on
Uh-huh.
that. The expected version, is that on a single aggregate?
Yes, so each aggregate has a specific version. And its version in event sourcing corresponds to the number of events in its stream. And so each aggregate has an ID, like the inventory item aggregate, a specific ID would be, inventory item dash a GUID or something like that.
Got it.
You could call them anything, and so you'd have that GUID and then an expected version. Let's see. So projections. Projections are a feature of EventStore specifically, and it's actually a very powerful concept. What they allow you to do is, in EventStore you have, so we're persisting all these events, and you could visualize the set of events for an aggregate as sort of like a stream, almost like a time series. And then you have multiple streams. You have a stream of events per aggregate. And you know, your aggregate is also a flexible definition, so you don't have to have, you know, you can have a stream that's shared by multiple aggregates, but for the most part it makes sense to have a stream per aggregate. A projection is something that basically takes a stream of events and projects it onto a new stream, or projects it onto something else. So how they're implemented in EventStore is you actually declare your projection with JavaScript, and you say, you know, with JavaScript, you know, take this event stream, and then when these events occur in this event stream, change the state and maybe emit a new event, and you can use them for all sorts of things, starting from implementing the query side of Cqrs. So you could have a projection that reads all the events from streams, like an inventory item stream, and maintains a piece of state that allows you to pull up an inventory item and get its name. Because if you saw here, we're not keeping the name anywhere. The name is part of these events, but it's not part of the state. But it is part of the events. So we could declare a projection that listens for these events, and whenever we have a created event and a renamed event, we update the name. And then the name is something that we could query directly. So this is an example of a projection declared in EventStore. What we're saying here is we're going to be reading events from the category inventory item. Now, how inventory items form a category is based on the stream names. So if you name your streams with inventory item dash GUID, then all inventory items will be in the category inventory item. The dash forms a category in EventStore. So this is saying, since we don't have a single stream for all inventory items, but we do have a single virtual stream that corresponds to all inventory items. This function here just says that this projection maintains state for each stream, not a single piece of state for all streams, but for each stream. And here we're saying that when we're processing a created event, which corresponds to this guy right here, then we're going to take the value that's in the body of the event. So again, this is state, this is event, and this is a function that produces a new state. We're going to take the value, and based on how I've serialized these events to EventStore, which is not the best serialization that's out there, but basically you can think of this as being the name. So what we're saying here is that take the name from the created event and save it to the state here, and then set isActive equals true. And these lines of code simply take this state and emit it to another stream. So what we actually have is we have another stream of events corresponding to each aggregate instance, but this stream has snapshots of the state. So to implement the query side of Cqrs, you can simply read the last event in that stream, and that's going to be your current state. The deactivated event, we simply set active to false and then emit it to a stream. Now all this code you can make cleaner and more reusable. So the idea is that you can use these to implement. You can use these to implement queries. So you can actually go and query EventStore directly. You could query something that this emits to. So you could query this stream with the read model suffix, and you can actually read your current state. So that's how your typical application would look like. Is when you query to print a form on the website, for example, you query the projection, you query the view, and you have views designed specifically for almost each screen. You can have some projections that are more or less generic, that could be used from a lot of screens, but a lot of times each user interface may have its own requirements, and you could create a projection specifically for that user interface such that it denormalizes and structures the data in a way that you can query it, without doing any sort of joins or anything like that.
A little bit like a view model.
Exactly, exactly. So I mean, a view, the terminology is not set in stone. I like to say that a projection produces a view model or a read model or a view. And a view in this sense is much like a database view, because with a database view you can join a bunch of tables together into one cohesive view. Now, in this case, we're almost like we're joining a bunch of events together into one cohesive view. So,
Sorry, when you're emitting, where are you emitting to? Is it then becoming something that's indexed in a way?
yeah. So you're emitting to, from the perspective of EventStore, you're simply emitting to a different stream. So in this case, the name of the stream is going to be this stream ID, which we prefix with read model, and in this case, this is no longer how I generate the ID, but basically you can think of this as you're emitting to a specific stream ID, and you can query EventStore for that stream ID, and that's like, that's a really fast query. It's sort of like a key value store in that sense. Give me this key, and it gives you whatever is associated with that key. So the idea is that we have an inventory item aggregate with a GUID, and we emit its projection state to a stream that also has the same GUID but a different prefix. So you could say, get me inventory item read model dash GUID, and it'll give you the state, almost like a key value store. And so these projections, as far as event sourcing goes in general, you don't have to have these projections in EventStore. You could actually subscribe to an event stream from C# or F# and do the projections there and output them to like a key value store or whatever you want to do with them. Or even SQL Server, because it provides indexing, all these things that are pretty convenient. Some of the challenges with event sourcing, also less tooling support. EventStore in particular is very kind of bare bones in terms of tooling. They have a little web UI, but other than that, not much tooling support. And this goes across the board for all NoSQL databases. You're not going to have the same kind of support as you'd have for SQL Server. There's nothing quite like SQL Server Management Studio out there for EventStore. So it's a challenge. A lot of times you'll have to be dealing with its REST interface directly. The benefit, though, is that it's a lot easier to automate things. There's a non-trivial shift in data modeling that you kind of have to partake in. You're not doing a relational data model anymore. It's not even a NoSQL type of data model anymore. You're thinking in terms of events. So you're not thinking about your application in terms of the current state, or when you think of a customer or a shopping cart or an inventory item, you tend to think of what's the customer's name, what's their email address. You tend to think of these static properties. Whereas with event sourcing, you think about the events. You don't think of a customer as some entity that has a name. You think of a customer as an entity that could be named and could be renamed. So you think about behaviors, not about static state. Queries must be implemented separately. So it's one of the big selling points of Cqrs that allows you to scale the queries differently, allows you to implement them differently. But the other side of the coin is that you actually have to do that. It doesn't come for free. So with EventStore, you could either do them using their projection framework, or you have to offload the events somewhere else and implement queries. Eventual consistency. Again, something that's common in a lot of the NoSQL stores, but the idea is that it's going to take a little bit of time for your query model to catch up, because it's not all done as a single operation. In SQL, when you update a table, it blocks the call until it updates all the indexes. And an event store allows you to persist the event, and queries are updated as a separate transaction, so to say. And this can also be tricky to deal with, because what do you do when you need the data immediately? So you have to devise various tactics to deal with eventual consistency. The other side of the coin, though, is that a lot of times you don't need strict consistency. You don't need immediate consistency. And the natural world, as it is a lot more eventually consistent than we've become used to with the SQL Server and fully ACID compliance. There's a lack of referential integrity. So in EventStore, or as far as EventStore is concerned, all your data is it's either JSON or some arbitrary byte array. It doesn't know what the data is like, so it's almost completely opaque. And this also goes for NoSQL databases like MongoDB, RavenDB. You have to manage your schema in a different way. And again, there's different ways of doing it, trade-offs that compromise. There's a lot of compromise that you run into, but overall, I still think it's a far more effective methodology. And so, again, refactoring, there's no such thing as, change the field name on all my events. Versioning, so there's no notion of schema maintenance. Versioning becomes actually interesting, but it becomes, I think the net result is better overall. Because versioning is, if certain events have occurred in the past, those events never really change, right? Nothing can argue with the fact that those events occurred. You may have new event types, well, those are just new event types, and that's fine. But the idea is that you can maintain your past schemas and your current schemas by simply just having them be different event types. And a lot of times that actually captures the changes that have occurred. So if you have a new event type, that's fine. You have to handle it, but you can also handle the older event types. Another way to deal with versioning is by creating a whole new stream. You could create a projection that takes an old stream and converts it to a new stream. So that projection that we saw earlier, instead of updating a state and emitting that, you could actually re-emit this event to a new stream and changing some of the values on it. That's another way to do versioning, is you simply start over with a new stream. And then you can actually have, what we've actually done is we've actually brought up a whole new application with a whole new set of events, and simply have the load balancer start pointing to the new application and discard the old application after all the events have been transformed. And that's also a convenient way to do versioning, by simply discarding the old data after having translated it to a new form. So we're kind of nearing the conclusion of what I had to talk about. To recap, these are the whys of F# and functional programming. No, the biggest thing with F# is that it's on .NET, and so it's easy to get started with it. The team that I'm on right now, they're mostly C# guys, but it's really easy for us to work together because somebody can write an assembly and I can use it from F# and vice versa, so you get full Visual Studio support. And the F# compiler has been open source for a while, so there's been some traction on getting the open source community to provide additional tooling for Visual Studio. So the part of the reason that things like rename and a lot of the refactoring tools don't exist for F# is that they're a lot more tricky to implement in F# due to type inference and a few other things, so that's why it's taken a while for things to catch up, but it's definitely going to get there. F# is multi-paradigm, and that's another reason why it's easy to get started with, because you could come from C# and you could start using classes and some new functional things in F#, and over time you evolve into a more functional style, whereas if you went and jumped into something like Haskell, you'd be lost coming from C# because it's a completely foreign environment. Type inference, as we've seen in F#, again, it could be a double-edged sword, but one of the benefits of it is that it can make your code a lot more brief, look a lot more like dynamic code, make it more readable in certain cases. Something we haven't really talked about, and this is a I don't know if this is an official paradigm, but the concept of language-oriented programming is that F# provides a lot of facilities for you to almost extend the syntax of the language. Now, you know, in C#, in the newer version, we have this await syntax, async await. C# has had that, or F# has had a similar thing since its beginning, and it's far more powerful, called computation expressions. And you can actually, with computation expressions, you can have different things happen depending on your implementation. So you can have asynchronous workflows, which correspond to roughly the TPL and the async await in C#. And that's one instance of a computation expression. You can also have a computation expression that does something different, that overloads this notion of a computation expression. And so you can really use the language to create a DSL for your domain based on these tools. For example, the same concept is used in F# to declare sequence expressions. So something like an IEnumerable in C# is a sequence in F#, and the computation expression engine is used to implement sequence expressions. Better coupling characteristics. So this really comes from the fact that the unit of coupling in F# and functional programming is your function. Whereas in C#, your unit of coupling is more or less ambiguous. You know, it could be an interface, an object, but more so an object. But the difference is that if you think about it, a function is, you can think of a function as an object with a single method on it. The difference, though, is that this interface is shared by everyone. So everyone has an interface. It's sort of like the func delegate in C#. Everyone has a reference to a func delegate of arbitrary length. And this allows you to couple functions or compose functions together from different libraries. You don't have to rely on an interface in some library. You just rely on the fact that it passes functions around. And this has a lot of benefits in terms of addressing something like the single responsibility principle. A lot of times you'll have a class that has a bunch of responsibilities, and like a perfect example is if you're familiar with controllers from the MVC framework, you tend to have a controller that represents either a resource or a set of pages, and the problem is that it has a bunch of methods on it that correspond to HTTP methods, but each of those methods is in many ways independent from its sibling method, but you tend to put them in the same class because it's convenient for dependency injection to inject a few dependencies into this class, and then the framework uses the methods to map to the corresponding HTTP resources. So it's convenient in C# to just push a bunch of functionality into a single controller, but then you end up with situations wherein a single action has to execute, but only one of the dependencies that this whole class has is needed, and so you end up with a violation of single responsibility. Whereas if everything is instead of function or oriented around functions, you don't run into those same issues. In F#, types are very cheap to declare, as you've seen, as compared to C#. You usually declare a lot of types in a single file. They take a lot less space, and this can address what in C# or object-oriented programming has been known as primitive obsession, where instead of declaring a type that represents an email address, you just use a string and so on. For things like age, you use like an int or something of the sort, and that's fine. But the problem is that you're losing a lot of the compiler static type verification. And in F#, it's a lot cheaper to declare types, so you actually end up doing that a lot more. You rely on the type system a lot more. As we've seen, it's more explicit, more declarative. You have pattern matching in the union types. This is a big one. You end up avoiding null references a lot more. F#, in fact, prevents you from creating a null reference to like a record type or a union type. You can still have a null reference to a type coming from C#, but you really don't run into the same null reference exceptions, because due in part to immutability, you never leave a value unassigned, and you can never assign it to null. Another thing with functional programming is that you really try to get rid of state, this whole idea of immutability. You try to avoid state, or you minimize state, you make it very explicit, you isolate it. Where in an object-oriented language, you use encapsulation to hide state. Whereas in functional languages, you eliminate state. You have nothing to hide. That's why you don't really use encapsulation in the same way in functional languages, because you don't really have any state to hide, which is really the only reason you do encapsulation in object-oriented languages, or for the most part. You're hiding some internal state of this object in order to provide a uniform interface on the outside. In functional languages, you don't really have state. So your data types you usually pass around as they are. And there are a lot of object-oriented patterns that are simply eliminated in F#. I actually wrote a whole blog post covering all the different patterns that are that you don't really deal with in a functional setting, or rather that are solved by elementary constructs in a functional language. Things like the iterator or the visitor pattern, single responsibility principle, all the solid principles, single responsibility, open close, the list of substitution principle, interface segregation, dependency injection, all those things, they don't even really come up explicitly in functional language because you don't have to deal with the issues resulting from, or the issues that cause those patterns to exist. And then I mentioned this briefly about how the functional paradigm is far more formalized than the object-oriented paradigm, and that means that there's a lot of research in various fields of mathematics that actually applies directly to your day-to-day programming in F#. Things like category theory. There's a lot of concepts in category theory that apply directly to functional programming, which I've actually used in implementing libraries. And the cool thing about that is you can look at your code in a different way. You don't think of it so much as a set of instructions for the runtime to execute, as much as you think of it as a specification of what you want your program to do, and the compiler sort of just fills in the blanks. So just a set of whys for event sourcing is that it's very simple and uniform when you really think about it. Is again, the interface to EventStore is you either read events or you save events. That's it. Compare that to something like SQL. Now, of course, you know they solve different problems, and you can't do everything you can do with EventStore that you can do with SQL. But again, it's very, very simple. The mapping is very simple. You just have to know how to serialize something. You don't have to map it to a table. Immutable. And this is a benefit. This can actually become a very explicit business benefit in terms of preserving information. And the project that I'm working on right now, this is actually very important because we want to be able to measure and report on everything that has happened in the system. Event sourcing provides a convenient way to do that because it's an automatic audit log. It's an append-only architecture, which EventStore actually takes advantage of in order to optimize reads and writes to EventStore. The way they've done it is actually the performance of EventStore on a spindle drive is almost as fast as it is on an SSD. So as you can imagine, if you're only ever appending, not changing anything, there's certain optimizations that you can make. And it's actually also very scalable. And the reason being is that your streams are really your unit of scaling, and you could, for example, take multiple event stores and shard your events across them if you use consistent hashing or something of the sort to make sure that you're always mapping to a specific instance. It's an easy way to do sharding since there's no relationships between the data. You can store inventory items, A through B on this event store, B through C on this one. Finally, once you get a hang of it, I feel like with event sourcing, it allows you to think about the domain that you're modeling in a more natural way. Because you can think about things occurring in the real world as things happening. And you sort of map that to what's going on, what are the events that are occurring, And event sourcing is a very convenient model for that. And I guess, okay, that's it. Questions?
Your team was mostly C#?
Uh, Yeah, they're mostly C#. There's a couple F# guys, and we're definitely looking to expand.
That's what I was going to ask. How do you do adoption of C# folks over to F#?
Well, I've been very heavily evangelizing F# at my place of work, and I mean I do that very simply by implementing something in F# that corresponds roughly to what we had in C# and just showing the benefits, much like I did here today. And everybody's really excited about F#. You know, in particular our CTO, he himself doesn't program in F#, but he likes the idea of it. He hasn't had the time to kind of dive into it, but everybody on the team is just fascinated by what you can do with F#. And so it's been sort of infecting the code base, so to say. More and more things are getting converted into C#, and then the C# in turn is becoming more like F#. So it is an ongoing process, because at the same time, while a lot of developers are excited about it, not all of them have the time, you know, to sit down and, because again, it takes time. I've been programming in F# for work for the past year, and I'm still learning things all the time. So it's definitely a process. It's not like, you know, coming to Java from C# or vice versa. So
No, it's a paradigm shift.
Yeah.
It takes some investment to get there.
yeah, and luckily I'm fortunate enough now wherein there's buy-in from the CTO, and we're looking to hire F# talent, and so that's really puts us in a good spot for F#. And in other organizations, I guess the main benefit or the main advantage of F# is that it's part of this, you know, .NET framework. So it's not much of a risk to get started with it. So.
Do you find, well, so two things about the change, the conversion to the shorter code. I've never had an opportunity to work with F# for any professional projects, but I feel like it's like if I had a solution, yeah, it would be so concise. But getting there, you spend so much more time thinking about it. It's like you spend the same amount of time thinking about what you're going to write. It's just that the end result is shorter, maybe. And
Yeah.
the second thing, if I can just ask it both at once, is for things like writing the guts of something, I can see really where F# it looks great for that. But the part of like interacting with the, you know, writing the Windows service or a website or whatever the entry point is to the application. I always kind of have a challenge with that, like how do I bridge the gap now into the real world?
Okay, so on the first part, you're absolutely right, and there is a bit of a somebody has said earlier on Twitter or somewhere that in F# you think more but you code less, and so there is a bit of that where you do spend more time thinking about how to express something in a functional way. Whereas in C# you probably just get started, kind of hack away, iterate. That is true, but over time you also get a feel for the functional approach to where you actually start to think in a functional way, and you think faster than you would even in a C# way, an object-oriented way. So it takes getting used to, but you do a lot more thinking, yes, with less coding. But over time you kind of get a feel for it to where, you know, you can be overall far more productive. And the reduction in code size is due in part, and due in small part, to the fact that F# is less verbose, as you've seen. There's a lot less boilerplate code. But for the most part, it's a consequence of the fact that when you start to think in a functional way, a lot of these problems that we have, or a lot of the code that you end up producing with C#, you simply eliminate it. I think the name John Graham, I think the guy behind Y Combinator, he has a very interesting but very deep quote about Java. He said, when you're programming in Java, you end up producing a lot of what looks like work. And again, because, you know, if you look at a typical Java stack trace, you have, you know, factory this, all these layers, which you simply don't end up having in a functional paradigm because you think of the problem differently. So that first part, and then what was the second part again?
Second part was just entry points, like.
Oh, yeah. So, so again, you know, there is an issue, like I was talking about earlier, that yes, interop with C# code can be a little bit awkward from F#. Something like, you know, Windows service. I don't know. I mean, like you could definitely do Windows servers in F#, but maybe because of the tooling support centered on C#, it might be more convenient to at least start in C#. Something like even like the ASP.NET Web API or MVC framework, because of the way that they've done their controllers, it doesn't really make sense to use F# for that. But on the other side, when I first started doing F#, I also thought about how, well, I'm probably going to structure my application in C# and then do specific things in F#. You know, you've probably seen this in blogs and Twitter where people say, you know, C# in the large, F# in the small, those kinds of things. And that's kind of where I started. But the more I did F# in functional programming, I just decided to do everything in F#. So again, it's a matter of time. You start to practice, you really get a hang of the functional paradigm, and then you don't want to go back again. So again, it takes time. So, any more questions?
You're located in another city?
Yeah, I am. I'm in the New York area, actually.
Thanks for coming.
Thank you for having me.
Thanks, Baba. I give you the tickets for you.
Thank
For
you.
the squads here tonight. So we have a couple of books here. Xbox, I don't know if anybody have time, but put aside here with a phone charge with one and one come with a light, which is pretty cool. I don't know if you have a dog, but it's very important in the evening when you walk it. Then I forgot I printed so I just read it here. One is a free ebook from Appress. Just if you want to just take it out of your email and give it back to me. One is a product from JetBrains. If you're a Sharpie.trace, you pick it up, enjoy it. So, and before, of course, we're going to go all to ping pong, I guess, for drinks after this. Next talk is going to be, of course, next month. I didn't come out with a date yet. And probably be the last week of March, a couple of speakers online. One thing that probably going to happen, we're going to have like a different structure of the meeting. We're going to start 6:30, 30 minutes, and kind of one-on-one talk for 30 minutes. In general talk, maybe like F#, basic, you know, language, syntax, or whenever you want to talk. Please come. And then after that, we're going to have pizza. And after 7, we're going to have the main talk. All right? Just to get more richness here. So, first in, first grab all the likes. So, 050. All right? Whenever you want. All right?
Each to his own.
047.
047?
Yep. Oh, thanks will be Line Medical. Oh yeah.
Thanks.
To guest us here and for the pizza, of course. 54.
That's me.
All right. I'm very enthusiastic about
Come with batteries or do I have to?
Oh, you get